Hello and welcome to the final in the series of Reigate Maths videos on the Travelling Salesman Problem for the second year Decision 1 unit for the A-Level Further Maths. This video is first focusing on how to find a lower bound and then how to combine the answers we found over the past few videos to find a set of values in which the optimal solution for our Travelling Salesman Problem could lie. Now, we only look at one lower bound algorithm, and that uses a minimum spanning tree method. So let's jump right into it. The first thing is what you're going to do is delete one of the vertices. Now, often you will be told which one to delete. And for this example, we're going to do that by deleting A. You can do this method deleting any of them. We're going to do it deleting A for the purposes of this example. So what we do is we completely remove A from this network. And then we find what's called the residual minimum spanning tree, which means the minimum spanning tree for what's left. So we're going to very quickly find the minimum spanning tree using Prim's algorithm here. I'm going to pause the video, I'll let you do it as well, and you'll be able to see my answer. So as I said, I've done Prim starting at B, but again, you could use any method. Now, quite often with this, they will give you in an exam as maybe a part A of a question, the grid or the matrix without A and get you to find the minimum spanning tree, then put A in and get you to use that to find the lower bound, so you're not doing the whole method again, possibly, no guarantee. So once you've found your residual minimum spanning tree and the length of it, we need to put the vertex that we deleted back in. So the way we do that is we look at the two shortest arcs from A. So two closest to A, which are AB and AC. AB is length 47, AC length 84. As you can see, I've drawn a diagram and I'm adding to it these arcs. I'll explain why once we're done. What you then do to find the lower bound is you take your residual minimum spanning tree and add these two lengths. And we get 907 miles. Now, why did I draw out the diagram? A, useful for finding the minimum spanning tree. But for the purposes of the Travelling Salesman Problem, when you are finding your lower bound, if this method finds a TOR, so if instead of, let's say, AB, we got AD as our next shortest one, this would form a TOR. If it does, that is the optimal solution and you have found it. Because there is no possible answer smaller than the lower bound. The lower bound gives you the best possible, the least possible number it could be. If that least possible number forms a TOR, then that is the answer. The problem with this lower bound method is it doesn't do that reliably. So that's why it's quite useful to draw it, because that could be a question is, explain how you know that this is the best option. Well, it's because my diagram, my lower bound forms a TOR. This one doesn't. So this is not a feasible solution. Okay, the length of the optimal TOR is not going to be 907, but we know it's going to be bigger than 907, which is what the purpose of this does. So what I'd like you to do is pause the video now and repeat the process, finding a second lower bound by deleting G. When you come back, start the video again, and then you can see what the answer should be. So you can see here the answer if you delete G. So you can see we've now got two different lower bounds. Neither of them are feasible because neither of the diagrams formed TORs, but we need to choose our best lower bound. So our best lower bound is always going to be the highest one. So we're going to pick the 971 miles. So the last thing we have to do is find the solution to the travelling salesman problem. Now don't forget, we might not be able to find the exact solution. One thing you can check, as I said, is if the lower bound forms a TOR, then that is the optimal solution. If you find that your best upper bound, which is the smallest, and your best lower bound, which are the biggest, give you the same number, that is the solution. Even if your lower bound didn't find a TOR, which in that case it would, that is the value. In this case, neither of those things are true. So all we can say is that the length of the optimal TOR, which we're going to call T, must be in the interval 971 to 1,233 miles. Key thing here is this lower inequality. We've shown that the lower bound the best lower bound is 971 miles, but we've proved that it can't be that because that lower bound didn't find a TOR. So T can't be equal to 971, but it can be greater. Whereas it could be equal to 1,233 because this is a feasible solution. This one gives us a correct answer, just not necessarily the best one. And that's the travelling salesman problem. As I said, sometimes you will be able to find an answer to this. Sometimes this inequality is good enough. Students don't like that, but sometimes heuristic algorithms are just the best we've got. Thank you for watching.